Hey, everybody, this is Larry. This is April 26th uh, of the Leetcode Daily Challenge. I don't know. That came out awkward. Hit the like button, hit the subscribe button, join me on Discord. There's only about a week left, so let me know how you feel about this in general. And today's problem is furthest building you can reach. I start these live, so, if it goes a little bit slow, just fast forward or skip ahead, watch it on 2x, whatever you need. Is this Rick and Morty? What is this? What is this animation? Hopefully that came through. But okay, let's actually read the farm first. How much time did someone put on that? But okay, well done, well done. Okay, you're given heights of the building, bricks, and some ladder. You start from 0 and you move to the next one using either bricks or ladders. When moving from I to I plus 1 to adjacent one, if the height is greater than or equal to the next building's height, you do not need a brick or ladder. That makes sense. So you can go down for free, or if it's less than the height, you can use one ladder or the difference in bricks. Okay, you could. So okay, so we're given 5 bricks and 1 ladder, and we're trying to solve all of these. Okay. Let's see. I mean, this feels to me like some sort. Okay, let's look at constraint for a second. So we are going to have 10 to the 5th item. So we don't really have to do something a little bit not dumb. This feels a little greedy, meaning that when do we use the ladder, and when do we use the bricks, right? Let's see. Well, okay, I think I have an idea. So basically, the idea is that you can go back in time, or um, you can use. So I mean, I think you can do it in 2 different ways, but both of them is the same concept of greedy. And what I would say is that, for example, you can just always use ladders, and then if you run out of ladders, you can kind of go back in time and substitute a ladder for a brick. Um, and the reason why that works is that, for example, I can't get over this animated game, but yeah, for example, here you go up 3, but then maybe later you only need to go up 2. And if you keep track of all the minimum numbers, then you're just basically going back and saying, okay, I'm going to use the ladder for the most expensive brick operation, right? And that's basically what you're getting into it. Because okay, so the idea is, and maybe another way of phrasing it, but you have to do the, so okay. So for this problem, you have to return the furthest building index. But for now, let's do a similar problem, which has this as a subproblem, or the other way around, which is a subproblem of this. Of okay, let's say you can always go from the beginning to the end, right? If you could always go from the beginning to the end, you're gonna use, and let's say you have no ladders, and or not. Don't say you have no ladders, but you have. Let's say you have, you don't care about ladders yet, and you only care about bricks. And I'm just making up random numbers, but let's say, it takes 4 bricks for the first jump, 2 bricks on the, dot, 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 right? So like you just have random numbers of how many bricks you need for each of these jump. And then now you try to figure out, okay, now you have, K ladders, say. You have K ladders, and you try to figure out which one to use. Well, then it makes sense to always use the most expensive one, right? And in this case, this is 8. Let's say you have 2 ladders, then you would use 8 and 7, so that if your K is 2, then this would be your answer of number, the minimum number of bricks you can use, right, using those ladders. So that's basically the intuition there. But this problem, however, it's going to be slightly more complicated because you want to return the furthest. And so it becomes, in a way, a query problem, in that you keep on going, and in a way that is sliding window, is that, it's not sliding window per se, but let's say, you could move 6 steps, and then now you have another number, right? Um, well, now that you have another number, now you have to update it in a good way. So that's basically the intuition that we're going to do, and I'm going to implement it, and then we'll chat about it as we usually do. Hopefully that makes sense. Okay, so how am I actually implement this in terms of data structure, right? I'm inclined to use a sorted list. I think that makes sense, maybe. Uh, so yeah, how do I want to use a sorted list? So basically, let's say we keep on adding all the gaps. We have one ladder, so we will have the prefix of the first. Um, can you even use binary index tree if you want? Yeah, I think you can. Yeah, you can use binary index tree if you want. Maybe that's a little tight actually. But in theory, conceptually, just throwing a prefix on the heights, and then but I'm not gonna go over that. Think about that as an upsolving thing. So let's say we have a sorted list and we want the prefix, right? Well, maybe that's a heap because we always want to. What do we want to do? Basically, yeah, I think a heap is what we're gonna have here because basically what we keep on saying is um, okay. What are we saying? We're gonna rephrase this a little bit, right? So ladder so ladder mean so we're just gonna okay. So we're gonna keep track of the things that we're using on the ladders, and we want to use the most expensive. Say k is the number of ladders, the most expensive heights, and then when we don't even need a sorted list. We keep things in a heap, and when we have a heap, we basically remove elements that are smaller than the most expensive elements. So this is going to be a min heap because you want to get rid of the smaller objects and you want to keep track of a heap of size ladders. Okay, I think that's basically how I'm going to do it. So I think that's right. That's oops. Yeah, and then now for mm, okay, so we only need to care about the adjacent ones. So I'm gonna do something like this, just to look at adjacent numbers. And then if x is greater than y, we can continue because that doesn't do anything. Oh, I guess we should also index this. Yeah, then we can keep going. Okay, and then oh, and this is Leetcode as well, because if it's Leetcode, we don't do anything. Otherwise, delta is equal to y minus x, because y is bigger than x. And then now we push this into the heap. Delta, I think that's fine. And then now, I always write these as while loops, even though I know that you only push one item at a time, so this is only going to happen once. And technically, it is a little bit more expensive to set up a while loop than a for loop if you want to think about bytecode and stuff like that, or opcode operations or whatever. But I just I like to think about writing these in the same way every time, and I don't have to think about it, even though I just did. But in theory, that's what I would say. So while this is true, what are we doing? Oh no, this. Oops, sorry. While this is greater than ladders, we want to pop, and then we set we subtract that from the number of bricks. Okay, and then if bricks is less than 0, we return index. Oh, I think index minus 1 maybe, that you can reach. So this would be index minus 1. And that's pretty much it, I think. You might have to go all the way to the end. So all the way to the end is just either length or length of height minus 1. I don't know how they phrase it in this one. Yeah, I mean, because the last element. Yeah, okay. I think maybe that makes sense. Let's give it a quick run just to see if this works. Um, Hope this is just off by one and not totally wrong, because I feel like this is mostly right, maybe. Okay, so maybe I am just off by one on this return index minus one. Uh, hmm, why is that? Oh, I see. Um, this is index because I was thinking about index being the y element, but it actually the index here is the x element because of how I did the step. So that's just a little silly. On my part, is that everything? Let's just do a high giga one. Can that be true? No, but yeah. Okay. Yeah. Okay. I think this is mostly good now. But yeah. Okay. Looks good. Let's give it a submit. Cool. Yeah. So that looks good. And what is the complexity of this? Well, I'm going to hand wave some stuff here because I write this in a zip kind of way, which is unnecessary. So that does requires extra space. Um, However, um, if you just use pointers, which is what people should do, like for indexes is in range of n or something like that, then this is O of one, so we can ignore that. H is going to be take O of ladders, which is linear time in the worst case. So either O of n or O of k, if you want to call it that, uh, because that's a k size heap because we keep it under k. And in that case, so this loop has n elements, or n minus one elements if you want to be more precise, and this takes well, heap will contain at most ladders equals k, let's just say is k elements. So this is O of log k, and this is O of log k. So all in all, this is going to be time is equal to O of n log k. Um, and as I mentioned, uh, this is going to be O of k or n in the worst case. It is technically min plus k, min of nk. It's fine. I know that technically I use more space here because I use zip, but like I said, you can do it in a cleaner way. Try to do it at home. But yeah, but that's all I have. Let me know what you think. Yeah, I think that's all I have. Yeah, I am. My eyes are very tired. So let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Hope y'all have a good day, have a great night, have a good new week. I will see you later, and to good mental health. Bye bye.